Hi guys, in this video we're going to be talking about how to do some of the calculations that deal with pendulums. So when we're talking about simple harmonic motion, that is oscillation. The two most common simple harmonic motion oscillators are masses on springs and masses on strings. We will be focusing on strings, which is pendulums. So we did the lab and we saw how when you release the pendulum, it creates a simple harmonic motion. What we're going to do in this lesson is we're going to start out by doing a little bit of review of some of the concepts that we've done along the way and how those play out in pendulums. So first of all, it says a 2 kilogram mass is hung on a massless 1 meter long string. If the string is held at a 15-degree angle from the vertical, draw the free body diagram for the mass. So again, that is a review, but what we have here is, let's draw our vertical line. But what we have is our mass is being pulled at a 15-degree angle. Okay, so here's a diagram of what's going on. Let's take that 2 kilogram mass and draw a free body diagram. What are the forces acting upon that mass? Well, of course, we have the force of gravity acting downwards. And then the other thing that we have is we have the force of tension acting at this 15-degree angle. And so here's what our free body diagram looks like so far. But of course, this is not an equilibrium because we've got this extra x component over here. And so we're going to draw a little bit of an x component over here, and we're going to call that the applied force. That's you holding the pendulum in position. Okay, let's look at question number 2. Assuming the mass is held at rest, calculate the force of tension in the string. So we have this force of tension. We don't know what it is, but we do know what the force of gravity is. And if we know what the force of gravity is, that's going to equal this component, which let's just call this Fty, because that's the force of tension in the y direction. And so we could say that Fty plus Fg adds up to 0. That is, the sum of the forces in the y direction is equal to 0. And so we're going back to this equation. So if I subtract those, then they have to be in equilibrium, right? What I could say is the force of tension in the y direction is equal to the force of gravity. Well, the force of tension in the y direction, I don't know what that is, but I know what the force of gravity is. It's mass times gravity. And so that is 2 times 9.8 meters per second squared. And if I multiply that out, I get 19.6 newtons. So the force of tension in the y direction is 19.6 newtons, but it's not asking for that. It's asking for the force of tension. And so I know that this is a 15-degree angle, and if that's a 15-degree angle, then I can do some math and figure out what that force of tension is. Okay, if I go back to trigonometry and I set up this triangle and I look at what's going on, I know my FTY, and that is 19.6, and I know my theta is 15 degrees. Let's stick with this, and we have the cosine somehow. So we could say that the cosine of 15 degrees is adjacent over hypotenuse. That is 19.6 newtons over the hypotenuse, which is F sub t. Now I just have to do this mathematically. Mathematically, we can switch these two, and we can say Ft is equal to 19.6 newtons divided by the cosine of 15. So take a second on your calculator, make sure you're in degree mode, and do that calculation and see what you come up with. Okay, and you should have come up with the force of tension is 20.29 newtons. All right, this is a little bit of review from first semester, which is good because we have the AP test coming up, so this is probably a good review for us. Okay, then let's go on to the next concept, which is another review question in a way. If the mass is no longer held at rest, what is the net unbalanced force acting on the mass? Calculate the magnitude of acceleration that this force causes. All right, if you look at this, and it doesn't matter which diagram, I think I like this one for now. If we let this go, what direction is it going to go in? Isn't it going to go in this direction? That is, it's got some gravity holding it down, but then it also has this centripetal force, which is going to be pulling it as well. And so the net force is going to be going in this direction. That's the net force that we need to be looking at and figuring out. Let me come down here and draw another diagram. I'm just going to basically repeat the same diagram, but bring it down here so we can use it again. Okay, so we have the force of tension acting at a 15-degree angle. We have the force of gravity coming straight down. We said that the net force now is going to be going this direction, pulling it downward and to the left. I could draw an equivalent segment here, couldn't I? And so I'm just going to do that because it's equivalent and it's just out of the way a little bit. It's going to be, I'm just going to draw it from down here. So we have this that we are working with. Now, you might remember from first semester that we did this thing kind of like an inclined plane where we kind of put our whole axis at an angle. That's what we're going to do. Let's put this axis at an angle and bring it down here. Now this should be a 90 degree, okay? This now is my y direction. This is FGY. And this is my x direction. That's FGX. Okay, FG is still the green one. FGY is coming down this way. FGX is going that way because I've taken my axis and I've tilted it. And that helps me to make the calculations a little bit easier, and that's why we do that. Okay, FGX is what we were just talking about. That is the net force or the restoring force. And what I mean by the restoring force is it's the force that's going to bring this pendulum back into equilibrium. Right now it wants to move, right? And if it settled down, it would eventually settle down right here, right? It's going to come down and stop at some point. So that is the restoring force, the one that's taking that pendulum back to the equilibrium point where it's not going to move at all. In other words, if nothing is holding it, it'll stay there. Okay, if we look at this FGX here, it is across from the 15-degree angle, right? There's my 15-degree angle. There's my FGX. So my FGX is across from. That means sine. I know that FG is mass times gravity. So this FGX is going to be mass times gravity times the sine of 15. Well, I did mg a minute ago. It was 19.6, right? So this is going to be 19.6 times the sine of 15 degrees. Take a second on your calculator and see what you get there. And you should have gotten 5.07 newtons. That is the restoring force. Now that we did our trig here, we've got the final answer. That is our restoring force. Now the second part of that question asks, calculate the magnitude of acceleration that this force causes. Okay, so if we set up like an F equals ma here, our F is our mg sine theta, which we just came up with, 5.07, which we could put it over there. I'm going to go back. Let me try a couple things. We're going to do one thing. We're going to say, let's just say it's mg sine theta, and that's equal to m times a. Well, the masses cancel, right? So now we just have g times the sine of theta is equal to our acceleration, and that's what we're looking for. So let's take that now. G 9.8 meters per second squared times the sine of 15 and see what we come up with. So use your calculator and see what you get there. And I'm getting 2.54, and this is acceleration, so that is meters per second squared. What I wanted to say a second ago is that maybe if you didn't do it this way, and instead you said, well, my restoring force is 5.07 newtons, is equal to the mass, which our mass was 2 kilograms, times acceleration. Let's see if that's going to be the same thing. And it is. It comes out to be 2.54 as well. So either way you had done it, you would have come up with 2.54 meters per second squared as the acceleration. Okay, question number 4. Again, we are still doing basically some review. I thought about not putting it in because we're in the situation we are, and it's like, just cut it down to the bare minimum. But this is important because it's review, and we have an AP test coming up. So all of this is going to be helpful to remember how we came up with some of these things from first semester. So based off the length of the string and the initial angle, calculate the maximum vertical displacement the mass will experience. Remember what we had before. I'm going to draw that same free body diagram. Actually, no, maybe not even the free body. I'm going to draw this diagram, and I'm going to replicate it down here. Okay, do you remember we did this before in first semester? If this string came straight down, it would be 1 meter long. If we pull to the side, guess what? It is still 1 meter. It's just at an angle. And so now what we need to do is we need to find out, okay, if that's at an angle, that's the hypotenuse now, then how long is this leg of it? That is, let's just find that piece, because then we'll subtract that away to find our delta y. And delta y is what we're looking for. And so again, if we look at that triangle, we know that's a 15 degree. Let's go back to our cosines. Let's go back to the cosine of 15 degrees is the adjacent over hypotenuse. The adjacent is what we're looking for. Let's just call it height for now. It's not really the height, but that's just going to be what I'm going to call it. So let's just call it adjacent over hypotenuse. That's height over 1. So the cosine of 15 degrees is just h. Let's find the cosine of 15 degrees on our calculator. And we are in degrees. All right, so I'm getting that the cosine of 15 degrees is 0.9659. I can maybe approximate that with 0.966. And that's this h value. But I don't want h, I want delta y. Well, delta y is 1 minus this. And so if I do that on my calculator without the rounding, and maybe even with it will be the same, I get 0.034. And that's meters. That tells me how high this bob has come as I pull it over. I'm pulling it over this way. It has risen 0.034 meters, 3.4 centimeters. Guess what that's going to allow me to do? That's going to allow me to calculate some energy. And that's the next question. Okay, do you remember LOL charts? LOL was basically we have kinetic energy and we have gravitational energy. We have kinetic and we have gravitational. And the kinetic energy in this case starts out at 0, but it does have gravitational. But then when it comes down, it has kinetic but no gravitational. So in other words, the gravitational energy in the beginning is equal to the kinetic energy at the end. This question mentions energy, but the actual question is how fast will it be moving? And so that's going to be velocity, but we know that K is 1/2 mv squared. So first of all, potential gravitational energy, we might have to look that one up, but it is mg delta y, or mgh. I don't remember which way it is on your on your AP sheet. It's one of those. Our kinetic energy is 1/2 mv squared. So if we solve this, we can cancel out our m's. And we're supposed to be solving for velocity. So we can multiply this times 2 and then take the square root. So we have 2 times g times delta y. We take the square root of that, and that will give us our velocity. You might remember this, and now that I have written it, when we had it before, we typically used an h, 2gh. But since I was up here talking about this as h, I just call this delta y to clarify. But it's the same thing. You might remember that. That's one that's not on your AP sheet, but it's a good one to have in your head. And so we put that into our calculator. We take the square root of all of that, and we get 0.816. And that is in meters per second. So again, just to reiterate one more time, this page was a lot of review from first semester. We did a little bit on pendulums in first semester, and so I wanted to come back to that so that we could see that review. Now, let's turn the page. All right, continuing with our concepts in review. Technically, the mass is moving in a partial circle. Calculate the net unbalanced force acting on the mass at its lowest point in the circle. We call this point the equilibrium point as its location with a linear acceleration of 0. Okay, so if we have our pendulum hanging down here, it's moving in this direction, right? That actually is a partial circle, wouldn't you agree? So we have a circle going on. We're going to have centripetal forces. Centripetal force is mass times centripetal acceleration, and that's on your AP sheet. But we talked about how centripetal acceleration is v squared over r, which I believe is also on your AP sheet. And so we can combine those and say centripetal acceleration is mv squared over r. This one's not on the AP sheet, but it's a good one to memorize. So now we can figure out our centripetal acceleration. So our mass is 2 kilograms. Okay, as long as we're doing review, we can also do some review of our units. This is our mass. This is our velocity that we just figured on the other side. Our radius is 1 meter. That's the radius of this circle that's moving. So now we have, and we square that, so now we have, if I multiply these numbers together, okay, so I square my 0.816, I take that times 2. That gives me 1.33. Looking at my units, I have a kilogram, I have a meter squared over second squared, and a meter here. This meter is going to cancel with this meter and leaves me with kilogram meters per second squared. I'm going to write that down. If we look at kilogram meters per second squared, a kilogram is mass, and meters per second squared is acceleration. That's our measure of force. We measure force in newtons. So this is 1.33 kilogram meters per second squared, but we call it 1.33 newtons. That last part about the units was just a little bonus. Number 7, as pendulums go through simple harmonic motion, the net force and therefore acceleration acting on the mass changes. Where is this force the largest and where is it the smallest? Force and acceleration are directly related to each other. So wherever the force is the greatest, the acceleration will be the greatest. So that's what they're asking here, is where is the force is going to be largest, or where's the acceleration largest, and where's the force going to be the smallest? So I'm going to draw my pendulum. I'm going to kind of draw a couple of them here, okay? All right, I have a hard time drawing straight lines apparently, but here, here's the pendulum in different places along the way. Where is that force going to be the largest, and where is that force going to be the smallest? Well, this is kind of a complex question. I'm going to post a couple of GIFs that might help you see this. But maybe something else to think about is, where is it going to be the fastest? Okay, isn't the bottom going to be the fastest? And that's velocity. I'm talking about velocity. Because what's the velocity at the top? Isn't it 0? So the velocity up here is 0. It comes down here, and now it is the largest velocity, and then it goes back up here to 0. Okay, the acceleration is actually the opposite. This is the 0 acceleration. However, up here is going to have the largest acceleration and the largest force. And one way maybe to think about that is, on each of these, don't they have a force of gravity? All of these have a force of gravity going down. And isn't it the same on each? That is, the force of gravity is going to be the mass times gravity on each one of these. But yet, there is also, on the top ones and the middle ones, but not the very bottom one, there's also a centripetal force, right? There's another force pulling it along. And that centripetal force is the greatest up here, because it comes down to here, and down to here there's 0. There's no centripetal force here. So the greatest centripetal force is at the top, and that means that has the largest total force, because all of them have the F sub g. This one is going to have the gravitational force and the centripetal force. So the force is largest at the top, and is going to be the smallest at the bottom, which means that the acceleration is going to be the largest at the top, and the acceleration is going to be the smallest at the bottom. And again, I will try to post some GIFs on that. Okay, so like I said, all of that was review. This is the new part. We now have a formula for the period of a pendulum. We basically talked a little bit about this when we did our pendulum lab. But let's just take a look. Since the force, acceleration, and velocity of a simple harmonic oscillator are always changing, we need a different set of equations to calculate the period, the time for one full oscillation, and displacement with respect to time for simple pendulums. So here is our formula for the period, where L is the length and g is the acceleration due to gravity. The horizontal displacement is how far it's moving left to right. On the problem we just did a minute ago, we looked at the delta y, and that was the vertical, but now we're talking about the left to right. And there is a formula for that, and it is given on your AP sheet, and it is x equals a times the cosine of 2 pi ft, where a is the amplitude, that means the maximum displacement, f is the frequency, t is the time, and x is the horizontal displacement from the equilibrium point. And when we do our calculations, this has to be in radian mode. And remember, another thing about t is, frequency. Frequency is also 1 over period, or capital T, but that's something to consider as well. Okay, just to take a second to show you on your AP sheet, here is the formula that we're dealing with now. This is the horizontal displacement, amplitude times cosine of 2 pi, frequency times time. This is the period of a pendulum, 2 pi times the square root of L over G. We will be dealing with springs later on in this unit, so this is the formula that you'll use for springs. So if you want to look on your AP sheet, this is where you'll find these equations. Okay, this now is going to be much more direct as far as that other stuff, like I said, was review. I feel like it's important to review because we do have the AP test coming up, but this is going to be more direct. We're just going to use this formula and see what we come up with. The period of oscillation is going to be T. I'll use a sub P for pendulum because that's the formula we're looking at, is 2 pi times the square root of, okay, mass. We learned in our lab that we don't care about the mass. It plays no role here. What we do know is we know that this is our length, so that is a 0.5 meters, and our gravity is 9.8 meters per second squared. So now we can do this calculation. So let's just plug that into our calculator and see what we get. I'm getting 1.42. These meters cancel each other out. These seconds we take the square root of, and it was in the denominator of the denominator, so now it is in the numerator. It is 1.42 seconds. We are looking for period, and period is a measure of time. So that works out for us. Okay, the frequency of oscillation, this is what I was talking about a second ago. The frequency is 1 over the period. And so we're just going to take 1 over that number and see what we get. And so I'm getting 0.705. And that is measured in hertz. Waves and sound is something that typically we would study next, but we probably won't get to it this year. And so just so you know, frequency is measured in hertz, and you might have heard that before. Okay, 4 seconds into the oscillation, how far from the equilibrium point is the mass located? What we didn't know, and we need to in order to figure this out, is the amplitude is 10 centimeters. And let's think again about what the amplitude is. The amplitude is the maximum displacement from the equilibrium point. And so here's our pendulum, and it's going back and forth, and the 10 centimeters is from here to here. That's our maximum displacement from the equilibrium point. But we're asking about, okay, 4 seconds, where along the way is it going to be in 4 seconds? And so that's what we're trying to find out. So we're going to use that equation. We're solving for x. Our a, we had to put it in there a second ago, is 0.1 meter. And then we take that times the cosine of 2 pi times frequency, which is 0.705, times time. And the time is 4 seconds. This equation is just going to be one that you're going to use off of the sheet. I mean, memorize it maybe, but just use it off of the sheet. To go through and derive where all that came from, I think might at this point be more confusing. So just know that this is the equation we're going to use. We're going to put this into our calculator. Our calculator does need to be in radian mode. So I put that into my calculator. I get 0.0426. Remember, that is meters. So we could leave it like that, but we could also say it's 4.26 centimeters. That might make more sense to us because we knew that this was in 10 centimeters. After 4 seconds, it has the 4.26 centimeter mark. And you could see how that might be helpful to know how far away it is in different situations. Okay, last question on this page. If the mass of the object is doubled, how does the period change? Okay, let's take a minute and think about what is the formula for the period. This is our formula for period. If the mass is doubled, I don't see mass in here anywhere. And we learned from our lab that mass does not affect period. So if the mass is doubled, how does the period change? No change. That is, mass does not affect the period. Okay, that is certainly enough for one day, so we will stop there.